Thank you for inviting me to give a talk here. In this talk, I'm going to talk about conjugate systems with respect to completely positive maps. From yesterday's and today's talk, you have seen there are two different approaches in free probability, non-microstates and microstates. Today, I'm going to focus on non-microstates via conjugate system. Then one thing a conjugate system tells us about a von Neumann algebra is the following. This is a theorem by Dabrowski in 2010. If there exists a conjugate system for self-adjoint operators x1 to xn, then the von Neumann algebra generated by this xi's is a vector. One motivating example that has a conjugate system is a free semicircular family. And in fact, the von Neumann algebra generated by semicircular operators is L of f, and depending on the number of the operators. And I want to generalize this theorem into the operator valued case. And in order to do that, I need to understand operator valued semicircular family first. This is defined by Shulatenko in 1999. Let B be a tracial von Neumann algebra. And eta ij from B to B be linear mappings from B to B with ij in a countable index set I. Then we define eta from B to be tensor of B of L2 I as this summation of ij at ij be tensor eij, where eij is a matrix unit. If this eta is normal and completely positive, we say this eta is a covariance matrix on B. One other result from this paper is that we can construct a von Neumann correspondence. Linear maps from B, yeah, just linear. Okay, we can construct a von Neumann correspondence denoted as this. Which is just span of B, E, I, B. This EI is just some vector that encodes the information of etas and close with respect to this inner product.
So I'm just a little confused. So what is, couldn't we have just said eta is a linear map between those two spaces that satisfies those properties? So what extra information, isn't every eta representable like this?
Yes.
Oh, okay.
And
So it's just notation. It's
yes,
not,
yes.
It's not a restriction on the, okay.
Then this inner product is B star, eta ij, A star C. This is what I meant by like the information of And this admits natural left and right actions of B. Then we can construct the full Fock space denoted as F tau, which is just L12 B tau, direct sum with this bigger space, D-fold B tensor product. Then on this full Fock space, we can define the left creation operator, which is defined as this. So what this does is it increases the length of the word. And it also has an adjoint. And this decreases the length of the words. And this is V-valued inner product, which is if A looks like A1 looks like A, E, J, B, then this is eta, I, J, A star, B.
I think you want A and then B on the outside.
Oh, yes. Thank you. Then now we can finally define V-valued semicircular operators. SI is defined as L of EIs and L of EI star. This is called B-valued semicircular operators. And this algebra generated by this polynomial algebra generated by B and SIs. It doesn't have a name. But by varying eta, you can construct a lot of good Neumann algebras out of this. For example, if B was complex numbers and eta was diagonal tau, then this gives us just regular, that we know, free semicircular operators. And this, in this case, this is Largent limit of GUs. And one other example is this can be Largent limits of random matrices, such as random band matrices. Or it could be some interpolated free group vector, or some tensor product, or some free product. one remark here is if this is satisfied, then this algebra is trivial. Okay. So now back to conjugate system. In this case, defined by Boyd-Glasgow, the semicircular operators have conjugate system, and the conjugate system is just itself. Then in what sense this holds in the operator case? We have to make sense of derivation and conjugate system. We are going to replace the complex numbers with B, and this scalar case will be just one special case. So we should expect many things we can prove in the scalar case should hold in the operator valued case. Okay, let's define a new derivation. Let M tau be a trivial polynomial algebra, and let B be a polynomial subalgebra, and X is a tuple of Xi's, where Xi is self-adjoint operators in M. And we assume M is generated by B and X. Then since it's trivial, there is a unique normal faithful conditional expectation E sub B from M onto B that preserves tau. Now we consider covariance matrix eta on B. And by composing it with E sub B, I'm still going to denote eta from M to B tensor of B of L to I. Then by the same construction, we have this object spanned by M E I M closed with respect to this inner product. Then finally, we can define a new derivation. Define eta partial derivative partial eta from B adjoint X to L2 of M tensor M box times M as a linear mapping that satisfies the following. Here B acts like a coefficient, so this should be 0. And partial eta xi is ei, and partial eta pq is partial pq plus p partial q, which is called product rule. Let's see an easy example. Partial eta of x1, b1, x2, x1. You apply partial eta on the first x1, then it becomes e1, and the rest just as they are. And b1, it's 0, so there is no term for that. And for x2, and the last one is x1, b1, x2, e1. Using this new eta partial derivative, we define a conjugate system. Xi in L2 of m tau is called a B eta conjugate system if it satisfies the integration by parts formula. Conjugate variable. And see if Xi exists for all I, then Xi is called B eta conjugate system. I forgot to mention this is for all P and Bx. More explicitly, if we look at this example, what this is saying is for P, x1, b1, x2, x1, Xi is tau of Xi x1, b1, x2, x1. And the right-hand side is ei, the inner product ei and this thing. And this is eta I1, 1, b1, x2, x1, eta I2, x1, b1, x1, eta I1, x1, b1, x2. And one remark here is when this exists, this partial eta is well defined. And closable, if you think of this as an unbounded operator on L2 of m tau. And in case of B equals to complex numbers and the eta being diagonal tau, then this conjugate system corresponds to the conjugate system defined by Voigt-Klosko. Back to semicircular family.
What do you mean by closable? As a subset of the Neumann algebra?
You can think of this as
It's a functional axiom of polynomials, right?
this from this Hilbert space to this Hilbert space. M.
So there is a dense domain.
Yes.
That notation E brackets X, those are, what is that? That's just polynomials, right? You
Yeah.
find the first instance of polynomials.
Yeah, these are.
As living in that. Okay.
Yes. Polynomial of x, i's, and coefficient with b. Okay. And I mentioned in scalar case, semicircular operators have a conjugate system, and conjugate variable for semicircular operators are itself. And this is true for this B eta conjugate system too. In scalar case, the way you can prove that is by cumulants in combinatorial way. And I was able to show the similar, they have a cumulant characterization using B-valued cumulants. But it's too technical, I'm not going to write the theorem down. But using that, we can show B-value semicircular operators have B at a conjugate system, and conjugate variable is itself too. And one other example is let n be m free products of phi of B eta. So this is B, the Neumann algebra generated by B adjoint X with amalgamation over B. And the Neumann algebra generated by B and S, where S are free semicircular family. And we think of this new operator xit defined as xi plus square root of t and si. And let t be the von Neumann algebra generated by this xit's. Then this new operator has a B at a conjugate system. And Ci in this case is 1 over square root of t, and Et of Si, where Et is a conditional expectation from n to nt. Okay, so far we have defined a conjugate system and seen some examples. Then can we recover Dabrowski's results? Assume that X has a B eta conjugate system, and eta is diagonal conditional expectation. Then the center of polynomial algebra generated by B and relative commutant of B is the center of B. And from this, we have one corollary. If xi commutes with B, then the center of M is the center of B. So this recovers Dabrowski's result.
Sorry, what does G mean? The center?
The center. And with the corollary in this example, I can say more about this. If xi commutes with B, since we already know Si free B-value semicircular operators commutes with B, then this psi t commutes with B. So in this case, the center of NT is the center of B. So whenever B is a vector, we can say NT is a vector. And one cool thing about this is since we perturb xi, this xi t could be inside of B as well. And I'm going to prove, I cannot prove the whole theorem. It's super long, but I will give some guidance. So since we have this new subject, I'm going to denote xi tilde as the conditional expectation onto B, relative commutant of B of xi's. And AI is the polynomial algebra generated by this one xi. And A is the whole thing.
The xi tilde in your AI?
Yes. Then step one is this partial eta, the closure of partial eta is densely defined on A. This is by convex hull argument from functional analysis. And step two is xi tilde has no atoms in B. That means there does not exist B in B such that kernel of xi tilde minus B is non-zero. And the next step is very interesting. A kernel of AI does not embed into B inside of AI. I'm using Popa's intertwining theorem. So I'm going to write down what that is here. AB inside of M, a trace of Neumann algebra. We say a corner of A embeds into B inside of M and denotes like this if one of the following is satisfied. There exist projections P in A and Q in B, and non-zero partial isometry V in Q and P, and a unidal star homomorphism theta from PAP to QBQ such that PAP.
Can you tell us what the corner of a von Neumann algebra is?
With a projection, yeah.
Okay, all right.
For all. And the second one is there does not exist a net of unitaries in A such that limit of conditional expectation of x u y is 0. And there exists, the third one is there exists A-B correspondence K in L2 of M tau such that it has finite dimension over B. So by using 1, if we assume it does, then we have a partial isometry with, so you can show the following. But from here, this VV star has to be 0 because it has no atoms in B, which is a contradiction because V cannot be 0. So
You're missing the parentheses.
and the next one is similar. AI does not embed, a corner of AI does not embed into B inside of A this time. How long do I have left?
Got 5 minutes.
Oh, gosh. And for this, you think of algebra as this. Nowhere. And if we suppose the opposite, if it does, since by 3 there exists a finite dimensional over K over B, AB corresponds K, and that K and the the projection onto AI, L2 of AI, are not centrally orthogonal in this algebra. Then by that, there is a partial isometry V that is smaller than a projection onto K and a projection to EAI. So V and VK is AIB correspondence with finite dimension over B. And then by this number 3 again, this contradicts the first part of step 3. And step 4 is to show there is no AI central vectors in L2 of A box times A. AI central vectors in here means if this is this, then it should come with all A i's. This is by using number 2 here. We can find if we have AI central vectors, we can find some unitary by using this, and we can make it small, so it has to be 0. And the last step is by considering a multiplication function that looks like this. What this does is it smooths out this partial eta, and this has a nice property that this converges to 0. And one other thing is this is bounded. And one can show this zeta of the commutant of xi tilde and any vector c in L2 of M is the commutant of xi tilde and x zeta tj c. So if we have...
Here you need I is not j, right?
Yeah, not the same. So if Z is the center of A, it satisfies, that means it commutes with everything in A, that satisfies this equalities. And this implies this vector is AI central. But by step 4, there shouldn't be. So that means this one should be 0. what this converges to Z. So what this tells us is Z is in the domain of partial eta J, and it becomes 0. Since Z commutes with xj2, the commutant of EJ and Z is also 0. By using this, then you can show 0 is this, and this is bounded below by the norm of Z minus conditional expectation of Z. Hence, Z has to be equal to EB of Z, which is in B. So for an element in the center of A, it is in B, and by the definition of A, the other way is immediate. I would stop here. Thank you.